Hi everyone, my name is Shelia Regan, and this is my HAP719 Module 3, Question 1, Teach 1. Um, there's an awful lot to this question. It's just one question, but there are multiple parts to it. So I started off with a summary of what the question is asking us to do. It's all about cleaning data. And of course, Module 3 is all about linear regression and other things as well, of course. But this is what we're going to be doing with this question. We're going to be cleaning the data and performing a linear regression analysis for medical foster home data. So, full disclosure, I did use Copilot to help me with the code for this. Um, and I'm going to go through it pretty quickly. I'm not going to break down the code like I would in previous, classes where we kind of talk about the functions and all of that. I'm not going to do that because there's a lot to get through. But I'm going to try and go methodically through each step and just kind of talk about what we're doing with cleaning this data and then the graphics that I got in my output and summary. So to get started, this script performs the following steps. Step one, or number one, the data cleaning itself, which are steps A through I. We remove rows with missing key variables, age, gender, and MFH, medical foster home. Um, Exclude patients with zero daily cost. We select relevant columns like cost, survival, age, gender, MFH, race, or disabilities. We convert categorical variables, race, into dummy variables, and then handle missing values. We also map gender to numeric. Binary numbers, they're male to 1 and female to 0. We convert all numeric columns to proper numeric types, and then we created a log transformed cost variable for normalization. For step two, we did some exploratory analysis, and it's item J in the assignment. We visualized the cost distribution and log transformed cost, checked the linearity between the age and the cost, and then displayed a correlation heat map and explained multi-collinearity concerns. Number three, regression setup, which are steps K through L. We defined our independent variables. There's lots of them. We added a constant term and clean our null and infinite values. We removed our constant columns to avoid singular matrix issues. And then we fit an OLS regression model using stats models. Number four, interpretation. We printed our independent and dependent variables. We identified statistically significant predictors. And, statistically significant would be anything with a p-value less than 0.05. We answered the key questions. Does age affect cost? Or does MFH, medical foster home, reduce cost of care? Then we displayed a regression summary and explained some of our terms. I also added a note explaining why the p-values appeared as 0.0000 because they're very, very small. Okay, so scrolling down, let's move into our code. So the first thing we started with was here, I just imported my libraries. I did a whole bunch. I didn't do them all at one time. As I was going through the code and things were coming up, I would I would just go ahead and put my import code at the top with the rest of them. So, and then also to try and get rid of any warnings, I imported the warning library. So next, for item A in our assignment, we had to load and clean our data. So here is my file path here. I actually did do some manual cleaning of the data file before I uploaded it. So for A, remove all cases in which all values for disabilities in 365 days, age, and gender are missing. So this is my code here for that. And then item B in the assignment, remove any row in which the treatment variable MFH is missing. So I dropped that. And I also added script. I came back and added script to print our results in the output. So item C, exclude patients who have had zero cost per day within the organization. That would not be valuable information to us. So we cleaned those up. Next, select independent variables. Item D, keep columns daily in org, days survived, age, gender, medical foster home, and race, plus our disability columns. Item E, check if cases repeat, and we drop those duplicates there. Next, convert all categorical variables to binary dummy variables. So this is my code for that there. And then I also printed the output for that. Item G, create missing value dummies for selected columns. And there is my columns to check and then to look for the missing values, missing value dummies. Okay, item H, gender is indicated as male, female, and here's where we are revising those by making them binary with male having being assigned 1 and female being assigned 0. Next, item I, make sure no numbers are entered as text. So I also did print out the final data types that we converted to. And then item J, create a log transformed cost, which you can see my code here. So next in the assignment, Dr. Alemi asked for us to do visual checks. So I created these plots. So this is the distribution of daily cost plot. But after I was done, I got an interpretation of each graph, and then I came back and inserted an interpretation, some interpretation text above each graph, so we can talk about it when I get there. So we have our distribution of daily cost, we have our distribution of log transformed cost, then we have our age versus daily cost, that's a scatter plot, and then for our correlation heat map, we'll see that I have an interpretation for that as well. Okay, so next for item L, we're going to do our regression setup here, and you can see the code. That's the setup for our regression, and then remove zero variance columns. And then also I did a variance influenced factor calculation because I had a high multi-collinearity values. So this, we'll talk a little bit more about this as well later. So that's my VIF calculation, and then we fit the model for our regression, our linear regression. And then I went back and added some text to our output for, this is an OLS regression. What is that? That sort of thing, why it's appropriate for this particular data set, and then log interpretation. How do we interpret these coefficients in a log transformed model? That sort of thing. Also did a summary of our the actual data analysis, the data cleaning, and then of the um, um, linear regression model. So you can see all of this are just things I put in there to talk about from the output. Okay, save output. So that's all of my Python data for the assignment. So now let's talk a little bit about the output. I wish I could make this bigger. Okay, so so when I ran this, this is what we got. Total patients in this data file were 16,006. Enrolled in the medical foster home were 2,459 patients, or 15.36% of the data. And there you can see my table of the dummy race values. And then I didn't really need to have this here, but I put it there, so I just left it. Numeric columns that were converted to numeric types. And then it just shows which columns. These are all of our independent variables. Okay, so let's talk about this first graph. So this is our distribution of daily cost. Um, it's kind of small, but we didn't have a lot of space to um, put this in here. But you can see we have the count there on the x-axis and on the y-axis, excuse me, and then daily in org on the x-axis. And the interpretation of this, as you can clearly see from that graph, the distribution of daily cost is highly right skewed. So most patients incur low daily costs, while a few have extremely high costs, up to around $8,000. This skewness indicates the data is not normally distributed and outliers may influence the mean. A log transformation is appropriate to normalize the distribution for regression analysis. And just a note, this was one thing that I did some manual cleaning of anything over 10,000. I I tried to remove anything over 10,000 just because of, for outliers, but obviously I didn't get them all. So let's talk about our distribution of log transformed cost. You can see a beautiful bell curve there. So this was a good suggestion that they made there. So the interpretation of this log transformed cost. So after applying the log transformation, you can see the distribution of daily costs is pretty normal. This improves our model assumptions for linear regression. It also reduces the impact of outliers and allows interpretation of coefficients as percentage changes rather than absolute cost differences. So next we'll go to our age versus daily cost scatter plot. So this is where, again, this is where I removed anything over $10,000. That's what, yeah. So you can see all these outliers up here. Age versus daily cost, days in organization, and then the age of the patient. So our interpretation of this, the scatter plot shows daily cost across patient ages. Costs are widely dispersed with no strong linear trend, indicating age alone may not strongly predict cost. Most costs are under $1,000, but outliers above 5,000 occur across different ages, suggesting other factors influence cost more significantly. So finally, this is our last graph. This is our correlation heat map, and you can see all of our variables there on both sides. Um, and let's look at our interpretation. This was hard to read. So I'm going to leave that there for a minute. So the interpretation, the correlation heat map shows strong positive correlations among disability variables, indicating they often occur together. Daily cost and log transformed cost are highly correlated as expected, but both have weak correlations with most predictors. Race dummies are negatively correlated with each other due to dummy coding. High correlation among disabilities may introduce multi-collinearity, which should be considered in regression analysis. So we did do a variance influence factor um, table for that. So as we see next. So next, we dropped our zero variance columns, our constant, gender missing, age missing, MFH missing, and days survived missing. So you can see our variance inflation factors here. And let's talk about what this means. So we dropped our high VIF columns. Okay, let's talk about the OLS regression table. So ordinary least squares is an OLS regression. It's a statistical method used to estimate the relationship between a dependent variable and one or more independent variables. It works by minimizing the sum of square differences between observed values and predicted values. In simple terms, OLS finds the best fitting line through the data points to predict outcomes accurately. So why would an OLS regression model be appropriate for this data set? So the dependent variable for us, which is our log transformed daily cost, is continuous, and the predictors are numeric or dummy-coded categorical variables. OLS is suitable because it assumes linear relationships, and the log transformation helps meet normality and homeoscedasticity assumptions. Talking about coefficients in our log transformed model. So I intentionally put this in here to help us interpret our coefficients. When the dependent variable is log transformed, coefficients represent approximate percentage changes in the original scale. So for small coefficients, you multiply by 100 to get the percentage change. For example, a coefficient of 0.210 means the MFH enrollment increases daily cost by about 21%. And let's talk a little bit about multicollinearity. So multicollinearity occurs when two or more predictors in a regression model are highly correlated, making it difficult to isolate their individual effects. So this can inflate standard errors, reduce statistical power, and then make coefficient estimates unstable. So we use the variance inflation factor, VIF, to detect multicollinearity. A VIF above 10 is often considered problematic, indicating that the predictor is highly collinear with others. So let's move on to our regression summary. So for our model summary, our OLS regression explains 0.629 of the variance in log cost. Adjusted R squared equals 0.629. The overall model is statistically significant based on 8,559 observations. Significant predictors where the p-value is less than 0.05 and their direction of effect. Our MFH increases our log cost with a coefficient of 2.475. Days survived increases the log cost with a coefficient of 0.002. Race B increases log cost of with a coefficient of 1.527, and then race non increases the log cost with a coefficient of 1.40 results, 1.402 as for the results. And here is a table of our regression results. And I'm not going to talk about each one of these. I just want to do a summary of what these mean. There are some notes there you can look over, but a summary of our findings, summary of analysis. So for data cleaning, we removed all those rows with missing MFH, age, gender, and disability indicators. We excluded patients with zero daily costs, converted categorical variables to dummies, and handled missing values, and applied log transformation to daily cost to address skewness. Visual insights for this, our daily cost distribution is highly skewed. Our log transformation improved our normality. Age showed a weak correlation with cost. Other factors are likely more influential. Disability variables are strongly correlated, suggesting multicollinearity risk. Our multicollinearity check, VIF analysis performed to detect multicollinearity. We dropped our zero variance columns and predictors with a VIF of greater than 10 to stabilize our model. Our regression results, model explains 0.629 variance in log transformed cost. Our overall model is statistically significant, and our significant predictors are MFH, days survived, race B, and race non. Interpretation coefficients represent percentage changes in daily cost due to predictors. MFH, medical foster home enrollment effect. We want to check the coefficient in summary for interpretation for that. And then our multicollinearity was addressed by removing high VIF factors. So I know this was a lot. So do feel free to reach out to me if you need any pieces of this or would like to talk a little bit more about why I set the code up like this the way that I did. But yeah, so this is my Module 3, Question 1, Teach 1. I hope you guys enjoyed that as much as I enjoyed putting it together. Thank you so much, and I look forward to hearing from you.